Okay, everybody, we are down to the last two topics. And the first of those two topics is called the ratio test. And what the ratio test is a more general way to determine the convergence or not of a series. So we've already seen the geometric series and the way to determine whether you've got convergence or divergence there. We've seen the P series, and we know how to handle it in those cases, and we've seen the alternating series test. Now we're looking at the ratio test, which is a little bit more general. It does have one downside that can happen. There's an inconclusive case that could result. But here is the ratio test. I'm going to just go through what it is, and we'll do a couple of examples. Here we go. The ratio test starts with a series, and we're going to call that sum of a sub k. It's a series with positive terms, and we're going to find a limit from that series. We're basically going to take the k plus 1th term, and this is in general, divided by the kth term. So we're going to look at these in general cases, and we're going to set up this ratio, and we're going to take the limit as k approaches infinity. So what happens when you take one term divided by the one in front of it, but you kind of work that through all the way out the series to k approaching infinity? And we're going to see if there's a limit. If that limit is less than 1, the series converges. If the limit is greater than 1, the series diverges. And unfortunately, that does leave us with this. If the limit is equal to 1, the test is inconclusive. So this is how we're going to do the ratio test. Why this works, I'm going to give an explanation for that in a separate video. So if you have some interest in why this is a valid test, I'll give maybe a little bit of motivation for why it works. This test is really good when you're working with exponentials in your series or in your terms and factorials in the terms. And we'll take a look at factorials, I think, probably in the first example. So while we're there, let's go ahead and take a look at an example. Here we go. First example up, we're looking at the series k is 1 to infinity of 1 over k factorial. We could start looking at this. That's 1 over 1 factorial plus 1 over 2 factorial, and so on. That's what we're looking at here. So that's 1 over 1 plus 1 over 2 plus 1 over 6. Remember, factorial is 3 times 2 times 1. 4 factorial, 4, 3, 2, 1, and so on. So this last term would be plus 1 over 24, and that keeps going. Now it may not be clear whether this thing is going to add up to some value or whether it's going to converge or it's going to go off and diverge to infinity. So here's what we do to work the ratio test. We take 1 over k factorial, and we're supposed to look at the ratio of the k plus 1 term divided by the k term. Well, the k term we've got. That's 1 over k factorial. What we don't have yet is the next term. Well, the next term simply comes from replacing k with k plus 1. And if we do that, we get 1 over k plus 1 factorial. So this is the ratio that we need to look at. And we need to then take the limit as k approaches infinity of this ratio. 1 over k plus 1 factorial all over 1 over k factorial. And it looks like, what are we supposed to do? How are we going to get there? Here's what we do. We're going to break down this piece of the problem, k plus 1 factorial. I'm going to take a look at that down here. K plus 1 factorial, if we remember what a factorial is k plus 1 times the term that's 1 below that. Well, that's k times all the way down to 1. But this is k times the next to 1. This is k factorial all by itself. So k plus 1 factorial can be rewritten as k plus 1 times k factorial. Let's take this and replace it here. we end up with this new limit. Limit as k approaches infinity of 1 over k plus 1, k factorial, over 1 over k factorial. Now remember how we divide fractions. We multiply by the reciprocal of the denominator. So this becomes k factorial over 1. Well, that allows us to do some canceling. The factorial pieces now cancel. And what we're left with is 1 over, limit. Let's do it right. Limit as k approaches infinity of 1 over k plus 1, because that's all that was left up here. And what we know about this is, as k approaches infinity, this is heading to 0. And for those who are getting this, 0 is less than 1, because the test, let me go back for a sec, the test for convergence is if the limit, which we just got, and the limit was 0, if it's less than 1, convergent series. Well, that's where we are. We have the limit is 0, 0 is less than 1, therefore, 3 dots, converges. Let's go ahead and look at the next example I have down here. And this next example says k over 2 to the k. So now we're dealing with an exponential type of function. We'll see how that plays out. Here's what we do. We take the k plus 1th term. So that's not k now, it's k plus 1. And it's not 2 to the k, it's 2 raised to the k plus 1. And all that's divided by the original term, k over 2 to the k. Here's what we do this time. We need to work with this exponential piece, 2 to the k plus 1. And we know we have rules of exponents. I can write this as 2 to the k times 2 to the 1. There's my k plus 1. So we're going to go back and rewrite the denominator of this upper term as 2 to the k times 2 to the 1. This is being divided by k over 2 to the k. Take this whole denominator, flip it up, and there we go. And what we notice is that our 2 to the k terms cancel. And what that leaves us with, because we need to look at the limit as k approaches infinity of this, is numerator k plus 1, denominator 2k. Polynomial over polynomial, highest degree 1, highest degree 1. So when we deal with a limit as k approaches infinity, look at the highest degrees, check the ratios. This limit is 1/2, and 1/2 is less than 1. Therefore, we have another converging series. 2 examples of the ratio test. I'm going to post 2 more videos. One is the motivation for why this test works, and the second one is going to be 3 more examples, a little bit more complicated than these 2. So look for those, but this is a good place to get us started. See you soon.